Good morning, ladies and gentlemen. My name, thank you, good morning to you too. My name, okay, so funny thing is, I could read this before you dim that light. So, could you bring it up just a wee bit? There you go. Thank you. You can actually do half that if you have the ability to dim it a little more. My name is Brian Kent Wallace. I have the honor of serving as treasurer for the National Society of Black Physicists, and I will be serving as your master of ceremony for our opening session. It's my pleasure to call the meeting of 2024 Joint Conference of NSBP and NSHP to order. This is a landmark conference, having only the second time our two organizations have held a conference together, and it is one of the largest conferences that we have had the pleasure of hosting. I would like to call at this moment for a moment of silence for the past and deceased members of our two organizations in remembrance, for it is their contributions to our organizations that have led to where we are today. With that said, we would like to have welcomes from various representatives that are part of this organization and those that have helped to make this possible. I would like to first call a representative from the University of Houston, who is our co-sponsor, to offer a few words.
Good morning. My name is Donna Stokes. I am a professor of physics, and I am also the Associate Dean for Undergraduate Affairs for Student Success at the College of Natural Science and Mathematics at University of Houston. I'm so glad to be here in front of you this morning. This brings back so many memories. In 1986, dating myself a little bit, I attended my first National Society of Black Students meeting, which is what it was called back then. And it just is so wonderful to see that this has continued. And I've attended the meetings over the years, and it's so great to see that we have the joint meeting again, which is a wonderful thing. How many of you are first-timers to this meeting? Awesome. This is wonderful. Woo. So I want to encourage you all as first-timers. As I said, when I came here to that first meeting in 1986, I was a junior at Southern University, where I graduated. And I was very nervous and scared when I came, but it was very great to be here, to see other people who looked like myself, who were loving physics just as much as I did. So I want to encourage you, whether you're a novice or whether you're a veteran, to take advantage of the opportunities you have at this meeting to network with your peers, with industry leaders, with faculty from across the country. This is a great opportunity for you to start building the network that you'll need to move forward in your either graduate or professional career. And this is a great place to start and do that. I also want to encourage you to enjoy the city of Houston. It's the fourth largest city in the country. It is the energy capital of the world. We are home to so many restaurants. I don't even want to name how many we have, but it's a lot. Great food. We have a wonderful museum district, nice shopping, a few party places. Don't visit those too much. But so much to do in Houston, so I want to encourage you to take advantage of being here in the city. But also, while you're here, make sure you're getting involved in learning some great physics. There are some wonderful experts here in the room with you, and they all want to share what they've been doing in their research, so make sure you're taking advantage of that. So on behalf of the University of Houston, the Department of Physics, the College of Natural Science and Mathematics, I want to say welcome to you all, and I hope you enjoy the conference.
Thank you, Dr. Stokes. And let me apologize for not calling you by name. I was looking at the wrong part of the program. I would now I'd like to call to the podium Dr. Sarah Larson, Dean of the Graduate College of U of H.
Good morning, everyone. I'm Sarah Larson, and I am the Vice Provost and Dean of the Graduate School at the University of Houston, and I'm also a professor of chemistry, or physical chemistry is my specialty area, so close to physics. It is my distinct honor to welcome you all to this important gathering, a joint conference of the National Society of Black Physicists and the National Society of Hispanic Physicists. As Vice Provost and Dean of the Graduate School at the nearby University of Houston, it fills me with pride to see such an exceptional group of physicists, scholars, students, and leaders coming together. This conference is more than an event. It is a testament to resilience, excellence, and the pursuit of scientific discovery. Today, we celebrate your achievements, the paths you have followed, and the new ones you are forging in the world of physics. Adding to Professor Stokes' comments, I encourage you to connect and collaborate, share your ideas and challenges, and inspire each other during this meeting. Thank you all for being here. I wish you an enriching and transformative experience over the next few days. May your dialogues be insightful, your discoveries groundbreaking, and your network stronger by the end of this conference. Thank you.
At this time, I'd like to call the president of NSHP to the podium, Dr. Mario Boranda.
Hello, everybody. I'm really happy to be in Texas because I get to say howdy again. I graduated from Texas A&M, so this is really close to that place. And as president of NSHP, I'm really excited to be here. We've been planning for this for more than a year. We're going to be doing joint conferences from now on. We do have an awesome program for all of you. And for the students, I want to emphasize something that Dr. Paul Gay said yesterday. You're coming here, meet people, figure out if they have a program that you may apply for, and make sure that you leave with some offer of some kind. Maybe you might be looking for an REU, maybe you're looking for a grad program, maybe you're looking for a postdoc. This is a great place to do that. Meet other students. When you're a student, you might be like, well, my friends are sitting over there, so I'm gonna sit with them, right? No, go network with another table. Everybody do that and try to talk to other people so that your network keeps growing and growing and growing. And you never know, maybe you're meeting somebody that is gonna give you your next offer. So that's the main thing about this conference. So there's over 1,000 people here, 1,095, right? So that's awesome. Let's keep it going. And thank you for being here so early.
I would now like to introduce the president of NSBP, Stephen Robertson.
Good morning, everyone. These lights are very bright, and I don't have my glasses on, so all of y'all are kind of blurry. But anyway, welcome to this conference. We're very, very glad that you're here in the great state of Texas. Texas is my home state, so I'm trying not to duck out of here for Whataburgers and kolaches. Like Dr. Brunda said, we've been working on this for a year or more, and we're very excited to have all of you here. I want everybody to take full advantage of all the opportunities that are here. This is a professional conference, so it's not like We're just here just to have fun. We're here to learn, and we're here to grow, to find new opportunities and become new opportunities for other people. Back in the day, when I was a student, really all I really thought of is what I can pull from the conference. And what I've learned over time is the ability to give and the ability to do things for other people makes you valuable to those other people, and they want you inside of their network. So don't come up to people and be like, hi, I'm such and such, put me in your network. You should be trying to say things like, hi, I'm such and such, I do these things well, and I like doing these things. What do you like doing? And that your network kind of grows organically in that way. Take full advantage of everybody. Everybody's here. They're looking out for your best interest, even if somebody says something that's kind of not the best way you'd say it. We are physicists, so our social skills are not what they should be at times. But everybody is here for your best benefit, so just keep that in mind when you're here at the conference. Take advantage of every opportunity, and I look forward to meeting all of you while we're here. Thank you very much for coming. God bless.
Speak for yourself on social skills. So, I want to say, and this is from attending many conferences myself, that sometimes you don't give thought to what it took for this conference to exist. There's sometimes the assumption that, oh, there was a grant that made this possible, but once I became treasurer and had a very clear understanding of the inner workings of a conference, you would be surprised that only a fraction of our support comes from government grants. A good amount, a significant amount of the resources that give us the ability to put on conferences like this come from our sponsors and our vendors. So I would like you to please give a serious round of applause for the sponsors of this conference that give us the ability to put this on. Now, students, just this morning I was speaking with someone from the University of Boston, and it was like 6 a.m., so I was half asleep, but this actually stuck when we were talking. And he made an observation, and it came purely spontaneously, and he said, what I really enjoy about your conference is how student-oriented it is. It's not like a lot of the other scientific conferences. And I had not really considered that until he mentioned it, because when you're in the details of working through the minutia of putting on this conference, you're so focused on this conference that you sometimes lose sight of comparison to other events. And it is true that what makes our conference special is that we're dedicated to the advancement of the graduate and undergraduate students and postdocs by providing you with opportunities for summer internships and possible graduate programs, and for postdocs, possible employment. With that being said, the vendors are such an integral part of our conference because it gives us the opportunity to provide networking opportunities for students, both graduate students and undergraduates. So the flavor, the importance, the significance of our conference would not be what it is without the participation of our vendors. I would kindly like you to give a round of applause for our vendors. I now have the pleasure of introducing our student representative who will introduce our guest speaker. I would like to call to the podium Ms. Angie Urelta.
Buenos dias. As Kent said, my name is Angie Huerta, and today I have the honor of introducing the guest speaker, Dr. Carl M. Bender, who is the Konneker Distinguished Emeritus Professor at Washington University, but he is also a visiting professor at the University of Heidelberg University, the Imperial College of London, and King College London. He received his PhD from Harvard University, then went on to do a postdoc at Princeton. Aside from that, he was also the associate professor of mathematics at MIT and has been an Ulam scholar at Los Alamos, the editor-in-chief of the Journal of Physics A, and was granted fellowships from the Sloan, Guggenheim, Lady Davis, Fulbright, Leverhulme, and Rockefeller Foundations. In 2017, he was awarded the Danny Heinemann Prize for Mathematical Physics, and he is currently supported by the Alexander von Humboldt Simon Foundations and the UK Engineering Physical Science Research Council. Please join me in giving a warm welcome from NSBP and NSHP to Dr. Carl M. Bender.
Okay, thanks very much. Okay. Whoops, here it is. Okay, well, thank you for coming. I hope you enjoy the talk that I will be giving. I will be talking about mathematical physics, and I hope I can get you interested in some of the intricacies of this huge and rapidly developing field. So first of all, good morning. And just to acknowledge my financial support here, this is where it comes from. Okay? If you find what I'm going to say today interesting, there are two papers that I published this year. Here they are, and they will give a rather detailed summary of what it is I'm going to be talking about as it flashes by, okay? So here's the theme of this talk. Mathematicians find it enlightening to extend the real axis, that is real mathematics, into the complex plane. And in this talk, I'm going to extend Hermitian physics, that is real physics, to complex non-Hermitian physics. And you'll see in a moment what I'm talking about. What I'm going to show you is that if the Hamiltonian, remember the Hamiltonian defines what a physical system is going to do, if it is PT symmetric, the eigenvalues of the Hamiltonian can be real and time evolution can be unitary even if the Hamiltonian is not Hermitian. And to make sure we're all on the same page, P refers to parity or space reflection, and T refers to time reversal. Okay, so if you reverse space and time, that's the symmetry I'm talking about. Okay? And I think the most interesting development in this area that I've been working on is that in the complex domain, one Hamiltonian can define multiple phases having different physical properties. Okay, so very much like, there's one Hamiltonian that describes water, but water can occur in different phases. It can occur in a phase of ice or liquid or vapor, okay? And this talk is going to be organized in 3 parts. So here they are. There's a beginning, a middle, and an end, roughly speaking. Just to make sure that you understand the words I'm going to use, this is a very, very quick background of what I mean by PT symmetric Hamiltonians. So if you've taken a course in mathematical physics, the objective of such a course is to teach you how to solve problems. And there is one basic idea of how to go about solving a hard problem. I'll refer to that as an HP. You don't use an HP calculator, okay? You do mathematics, okay? So as an example of a hard problem, you might take the anharmonic oscillator, and that's the Hamiltonian p squared plus x to the 4. Nobody knows how to solve that problem. In fact, in physics, there are almost no problems you can solve exactly. Really, basically, no problems at all. You can count them on the fingers of one hand, the harmonic oscillator, the hydrogen atom, that's about it, the square well. So what you're told to do is not to solve a problem exactly, but to solve it approximately, okay? How do you do so? You use perturbation theory. And by the way, perturbation theory is PT, but that's not the PT I'm talking about. Okay, so there are 3 steps always. First, you insert a small parameter epsilon, okay? Epsilon is called a coupling constant. And this may require some cleverness on your part, but you insert this parameter epsilon in such a way that when epsilon is equal to 0, now you can solve the problem, okay? So here's the hard problem, and I'm going to put an epsilon over here. Why am I putting an epsilon in front of the x to the 4 term? Because now I can solve the problem if epsilon equals 0, okay? So that's the first step. The second step is you express the answer as a series in powers of epsilon. And that is a lot of busy work, okay? But you express the answer as a constant, and then a constant multiplied by epsilon, a constant multiplied by epsilon squared, and so on and so on. Okay, the third step is you have to solve the original problem. So you set epsilon equals 1, and you sum the series. That's it. So that's the recipe. It's really simple, right? So what's the big deal? The big deal is, well, not so fast, because it's very hard work to calculate the perturbation coefficients A, B, C. So you know how you do it. If you're a professor, you spend 15 minutes in the afternoon and you calculate the first term in the series. And then you bring in your postdocs, okay, and you say, calculate the next term. And they work all afternoon and they get B, okay? And they're really tired. And then you call in your graduate students, and they work for several weeks, and they calculate C. And then you bring in your undergraduate students, and you hire them for an entire summer, and they calculate D, and so on. And this is a lot of hard work. But it isn't deep work. It's just hard, busy work, and you have to keep track of the minus signs and the factors of 2 and so on. Okay, what's the real problem? The problem is, after you get done with this, the perturbation series that you're calculating almost always is divergent. So you have to figure out how you sum a series and get information from that series if the perturbation series is adding up to infinity, okay? And that is a very difficult problem, okay? But what I'm going to talk, and I'm not going to talk about that here. I mean, that's a whole course. But I'm going to talk about number 1, the first step, because it's not always easy to find a way to insert a small parameter epsilon into your problem. For example, if we take this problem here, oops, let's go back. If you take this problem here, where there's no x squared term, and you put an epsilon in front of the x to the 4, that can immediately, just by changing your dimensions of the problem, you can scale the small parameter out of the problem. And so you can't do perturbation theory at all. It's hopeless, okay? So there are a lot of problems that require great subtlety in finding a way to solve them. Okay, so here's an idea. And this is an idea that I've been working on for a long time. instead of putting a multiplicative perturbation constant epsilon into the problem, why not do something really strange? Why not stick it in the exponent? Okay, now I want to give you an example of this. Okay, so this is called the Thomas Fermi equation. That's not the subject of this talk, but let me just tell you, this describes the density of electric charge in an atom, in a neutral atom. Okay, now this is the equation that you have to solve. Okay, so I'm assuming spherical symmetry. And so this is just an ordinary differential equation, and it's short. It only has 2 terms. And you might think, oh, I can solve that. No, you can't. Okay? I mean, that is basically an impossible equation to solve exactly. And nobody knows how to do that. Okay? Now, there are boundary conditions, y of 0 equals 1 and y of infinity equals 0. And this is a well-defined problem. If you could solve that problem, you will win a prize. Okay? But there may be better things to do. For example, like tying your shoe or something. Okay? But can we solve that problem approximately? Yes, we can, because we can put an epsilon into the exponent. So I can rewrite this problem as y prime prime equals y times something to the power epsilon. Okay? And I know when epsilon equals 0 how to solve the problem. I hope you all do. How do you solve the equation y prime equals y, where y of 0 equals 1 and y of infinity is equal to 0? The answer is e to the minus x. I hope you all know that, or e to the minus r. Okay, and that's the problem that you have to solve when epsilon equals 0. And in fact, you can easily, on the back of an envelope, calculate a few more terms in the series in powers of epsilon. I'm not going to show you how to do that, but it's just busy work. And in 20 minutes, you can get an approximation to the problem that's accurate to about 99%. Okay, so perturbation theory is really, really powerful. Okay? Now, I want to go back to the Hamiltonian that I was talking about, this Hamiltonian. And so if I tried that idea here, I could put an epsilon in the exponent and write this problem. And now you see that if epsilon is equal to 0, this is the harmonic oscillator. As I told you, that's one of the few problems you can solve exactly. And now you expand it as a series in powers of epsilon, and that is a really effective way of solving that problem. But now I don't know, I don't know if you can see this. I'm going to try to write something on it. Let me see. So let me tell you a story. There is a school, there is a whole group of mathematical physicists working in Paris. Very, very distinguished group of mathematical physicists. I have visited them several times, and they include people like Isaacson and Brezin and Zubair, lots of people, one of them being Bessis, Daniel Bessis, and he's an old friend of mine, and an old friend of the guy who suggested that I come and talk to you today, Carlos Handy, who's sitting in the audience. And he told me that these guys were working on a very interesting problem, they thought. They were working on a problem in quantum field theory, which I'm not going to tell you about at all, okay? But the problem, they found a simpler version of the problem, which was a quantum mechanics problem, and this is the problem. This is the, well, let me write it. This is the problem that they had. They had a Hamiltonian, which is p squared plus I x cubed. Okay, that is the problem that they were looking at. And he said to me, what do you think about that? And I said, are you crazy? that is not a Hermitian Hamiltonian. And he said, basically, well, you're right. And he didn't work much on the problem. And I certainly didn't work on the problem. This is around 1993 or 1994. And that's basically all I could say about the problem. Can you bring back the transparencies? Yeah, thank you. Okay, so this is the problem, but you know, it's a stupid problem because the Hamiltonian is not Hermitian. But this is a funny story to tell you. I didn't work on the problem, but many years later, about 4 or 5 years later, I was in the audience of the worst colloquium I ever heard in my life. Okay, this colloquium was so bad at my university, it was so bad that it was orders of magnitude worse than the second worst colloquium I ever heard in my life. So this is really bad. And people were getting up and leaving, which is unusual because we have a very polite department. And I wanted to get up and leave, but the problem is I couldn't. And that was because I had invited the colloquium speaker. And because I was the colloquium organizer, and one of my friends in the department asked me to invite this guy. We weren't friendly afterward. But in any case, I couldn't leave, so I decided to escape intellectually and work on a problem. And for some reason, this problem popped into my head, okay? And I began working on it, and this is one of the luckiest things that ever happened to me because I found a way to solve the problem, okay? And what I did was to say, let's do perturbation theory. Let's put an epsilon into this problem. Let's consider working on this problem, okay? P squared plus x squared, you remember that's the harmonic oscillator. Anybody can solve that problem. Times ix to the epsilon. And I will solve this problem as a series in powers of epsilon, okay? And I said, the reason, at the time I said to myself, the reason we might do this is because the problem p squared plus ix cubed over here, that problem has a symmetry, okay? And you may know that when you do perturbation theory, you often break the symmetry of a problem, okay? For example, if you're solving a problem in electrodynamics, and you know electrodynamics has gauge symmetry, okay? But when you do perturbation theory, you may be violating gauge symmetry, and this is a difficult problem, and you have to take that into account. So what I did was to notice that this has a symmetry. That is, if I change the sign of x by parity, and I change the sign of I by time reversal, the problem remains invariant. You got that? You understand? Okay, so I calculated a few terms in the perturbation series, and I found, this is during, you remember the colloquium, the boring colloquium? It's not unlike this colloquium. So I found that all of the eigenvalues appeared to be coming out to be real. Now you must think this is ridiculous, because I thought it was ridiculous. How could a non-Hermitian Hamiltonian have real eigenvalues? And my immediate reaction, quietly, was to say, wow, okay. So that's what this talk is about. That was the beginning of the work that I've been doing. Now, I want you to, you remember there was an I in that problem. As you know very well, all of the great early theories of physics did not involve complex numbers. You know, the early physics are Newtonian and orbital mechanics, fluid mechanics, electricity and magnetism, relativity, There are no I's in any of those equations associated with those physical problems. The classical equations of mathematical physics are real. Okay, there are three basic equations. There is the wave equation, which is called the hyperbolic equation. There is the equation for equilibrium, which is the elliptic equation. And there is the process of diffusion, which is described by a parabolic equation. And physicists did not believe that what happens in the complex plane could influence what happens in the real world. Okay? I mean, that's interesting mathematics, but it has nothing to do with reality, and that's not even a pun. Okay? So, quantum mechanics, however, changed all that. As you can see, only look at the equation, please, but you can see that there's an I in this equation, in the Schrödinger equation. The Heisenberg algebra contains an I, and as Wigner pointed out, time reversal corresponds to a complex conjugation. And there are all sorts of quantum processes that involve complex mathematics, like tunneling. I mean, if I have a barrier over here and a particle approaches the barrier, classically it bounces back. Okay? But quantum mechanically, it can penetrate the barrier. But the particle is never inside the barrier. So how did it get to the other side? And the answer is it traveled through the complex plane. It left the real axis, went around, and back onto the real axis on the other side. Okay? So there are all kinds of appearances of I in quantum mechanics. There are complex amplitudes, and fermions use I. Okay? All of the descriptions of fermions. Okay. In fact, an electron lives on a two-sheeted Riemann surface, which consists of two complex planes cut and glued together. And so it turns out, if you put an electron at a table and you walk 360 degrees around and come back to where you were and look at the electron again, it's not the same electron. It has different physical properties. But if you walk around a second time, you come back to where you were. Okay? And this is remarkable. Okay? Walk around twice, and I want to see if I can demonstrate that to you. Okay, can you see this? Okay, I'm going to rotate this around 360 degrees. Okay, so watch carefully. This is pointing up. I'm not going to cheat. Okay, so I'm going to go around 360 degrees. Ouch, this hurts. Okay, but it's still pointing up. And this is not the same configuration because it wasn't hurting before and it's hurting now. Okay, now I'm going to go around another 360 degrees in the same direction, and we come back to where we started, and great, 720 degrees, I'm back to where I was originally. Okay? So, okay. So, can you bring back the, good. Okay, so just to make sure that you're with me, let me remind you what the complex plane is. These are some examples of complex planes. Actually, my wife and I traveled here to Houston on a particularly good complex plane. It was this one. This worked very, very well. There was only one minor problem with it. All the passengers were over here, but the toilets were over there. But other than that, there was no problem. Okay, so what I want to emphasize is that the complex plane and the real line have a completely different topology. Now, you may find this surprising, but it's true. So here, oh, whoops, let me go back. here is the complex plane down here. And this is called a stereographic projection to the complex plane. So I associate a point on a sphere with a point in the complex plane. I draw a straight line from the North Pole to a point on the sphere to any point in the complex plane, okay? And you notice that there's only one point at the North Pole, and that corresponds to the point at infinity. So in the complex plane, there is only one point at infinity. On the other hand, on the real line, there are 2 points at infinity. There's that way to infinity and this way to infinity, and those are 2 points. And this is very, very important for what I'm about to be telling you today. Okay? So what you are going to see by the end of the talk, if you can stand it that long, is that in both classical and quantum mechanics, one Hamiltonian can define multiple phases in the complex plane. This is a very radical idea that I'm speaking to you about. This is only stuff that I've been writing in the last year or so. And I'm going to illustrate this with a very elementary example, okay? So I'm going to discuss with you the Hamiltonian h equals p squared minus x to the 4. Minus x to the 4 is an upside-down potential, okay? You all understand that? This potential is an inverted potential. It's not a right-side-up potential that traps bound states. It's an upside-down potential, okay? And I'm going to show you, both classically and then quantum mechanically, that this Hamiltonian defines 2 completely different physical phases. One phase that lives on the real axis, and one phase that lives in the complex plane, which includes the real axis. Okay? And we're going to look at the classical Hamiltonian first. Okay, so you know what to do when someone gives you a Hamiltonian. You immediately write down Hamilton's equations. And I'm going to first talk about the phase that you know all about, that any undergraduate student would know about. You write down Hamilton's equations, you solve them, and here's an interesting question. If a particle has energy E, how long does it take for this particle to roll down the hill, the potential hill, all the way out to infinity? How long does it take to get to infinity? And if you do the calculation, what you find is that it takes this long. It's a finite number. Okay, so it gets to infinity in finite time. And you might ask, where does the particle go next? Okay, it takes time t to get to infinity. Where does it go next? Well, I don't know. It must stay at infinity. Where else? It's not going to roll back up the hill, is it? So it's going to stay at infinity for the rest of time. So what we have is this, as this picture shows down here, what we have is motion where particles starting at the origin roll down the hill to either to plus infinity or to minus infinity, okay? And these are called unstable motions. The particle rolls downhill and it goes off to infinity. These motions are parity symmetric. And let me explain to you why that's true, okay? If a particle is over here running out to infinity, okay, under parity, you change x to minus x, so the particle is over here. But you also change the velocity, which is a vector, which is pointing this way. You change the sign of that vector to a vector that's going this way, okay? And so this motion under parity becomes this motion, okay? And this class of unstable motions has a symmetry, and it's called parity symmetry, and these motions are all parity symmetric. Do you understand that? Yes?
Just to maximize your time, bear with me for 1 second. maximize your time. I do realize that there were some people that need to go to set up for your next thing, so we would just ask you to quietly go on to your thing, and we're going to truncate question and answer so that he can maximize his time to explain everything he's doing. And at the end of the session, if you want to ask questions, we're going to encourage you to come up to the front to ask. Sorry for the interruption.
Okay, okay. Okay, so let's look at what happens in the complex plane. There are 4 turning points. Okay, remember where are the turning points? If the particle is not moving, P is equal to 0, and all you need to solve is the equation that E is equal to the Hamiltonian. The energy is equal to the Hamiltonian, which is minus x to the 4. You solve that equation, you get 4 turning points. They lie in the complex plane. Here they are. If you start a particle that's moving in the complex plane, what does it do? It goes back and forth between the turning points, like a pendulum, except it's traveling in the complex plane. If you start a particle somewhere else, it goes around in a closed loop, like this. Okay? And I hope you understand that. So, in fact, all of the motions in the complex plane are closed loops. So what happens if we approach the real axis where you and I live? What will you see? Well, as you get closer and closer to the real axis, these loops get bigger and bigger and bigger. And when you reach the real axis, what is the particle doing? It travels all the way out to infinity. It loops around like this, and then it comes right back to where it was. Okay, this is a completely different picture. Okay, now it turns out that the amount of time for a particle to go around any of these closed loops is always the same, and the time is 2t. And indeed, if you start a particle on the real axis, it goes to infinity in time t, as we said. It then zooms around like this to minus infinity in no time at all because the particle is traveling infinitely fast. And then it comes back from minus infinity right back to where it started. So now the picture is completely different because this is not unstable. You start a particle at the origin, and it comes right back to the origin. Can you believe it? It's really remarkable. So again, let me show you with my fingers. If you have a particle going like this, okay, the motion that I've just described is PT symmetric. Not P symmetric, but PT symmetric. The particle is traveling out to infinity, and under parity, the particle is now going this way. Okay? Okay, and remember you have to reverse the velocity, so this velocity becomes that, under parity. But under time reversal, the velocity reverses and it's going this way. So the particle is always traveling in one direction. It's going out to infinity and coming back from infinity right back to where it started. So we have 2 completely different kinds of motion described by one Hamiltonian. One set of motions, one phase, is parity symmetric. That's the phase you know and would expect. But this new phase that I'm describing to you is PT symmetric, and the particles are bound. Okay, that is to say, they always come back to where they started. They're in a classical bound state. Okay? So yeah, good, thank you. So what we see on the real axis is unidirectional motion. The particle whizzes off to infinity, but amazingly, it comes back from minus infinity right back to the origin. Why? How can you go to plus infinity and come back from minus infinity? Well, I already told you the answer. Because in the complex plane, there is only one point at infinity, not 2. So if it's at plus infinity, it's already at minus infinity. Okay? So what I'm saying to you is quite new and quite radical. Okay, so you can ask, where is this particle most likely to be found? And as you know very well, when a particle is traveling rapidly, it's very unlikely to be found there. When it's traveling slowly, it spends a lot of time at each point, okay, so it's most likely to be found there. Since it's traveling rapidly at infinity, it's least likely to be found at infinity. And since it's traveling very slowly at the origin, it's most likely to be found there. And this is a picture, this is the probability of finding the particle. And you know what I'm saying is true, right? When you learn how to drive, your driving instructor told you that the probability of being found at a point is very low when you're driving rapidly, right? But the probability per unit distance. So you were told that as you approach an intersection, if you don't want to have an accident, you should drive as fast as you possibly can as you approach the intersection, because you lower the probability of your having an accident, okay? I'm going to get out of Houston as soon as possible, so I don't want the police to come after me. So a key point of this talk is that you can't just look at a potential and say whether it's attractive or repulsive. It might be both. And phases, these two different phases of motions that I've shown you, are distinguished by having different global symmetries. Okay, there are different kinds of symmetries, 3 in fact, that we could discuss. Complex conjugation symmetry in the complex plane is up-down symmetry. Parity means a reflection through the origin. So if you start here, you wind up here, okay? You go right through the origin. But PT symmetry is, first of all, P, so you start here and you go through the origin and you're here. But under time reversal, you change I to minus I, so you're here. So PT symmetry is left-right symmetry. Hermiticity symmetry, which involves complex conjugation, is up-down symmetry. And these are two very different symmetries. And until now, if you take a course in quantum mechanics, you only learn about hermiticity symmetry. And I'm talking about something really new and, in my opinion, really interesting. And that's left-right symmetry. Okay? So this is more mathematical, and I'm going to skip a few slides here. But I want to show you that in quantum mechanics, there are also two phases, okay? So I'm going to discuss exactly the same Hamiltonian, but I'm going to treat this as a quantum mechanical Hamiltonian that you might learn in a first-year undergraduate course in quantum mechanics. And suppose your professor says, let's study this Hamiltonian, and you say, gosh, I don't know how to treat a potential that is like minus x to the 4. But one way to think about it is, what do you mean by minus x to the 4? Well, you could say, I'm going to make a minus x to the 4 potential by considering a plus x to the 4 potential, and I'm going to multiply that by e to the I theta. And I'm going to let theta go from 0 to pi, and you know that as theta goes from 0 to pi, this changes sign, so v goes to minus v, so we're now talking about a minus x to the 4 potential. Okay. Well, I'm going to skip, as I said before, a few slides, but I want to show you what ends up. What ends up is that as you increase theta from 0 to pi, the eigenfunctions that you started with that were vanishing at plus and minus infinity are now continuing to vanish, but they don't vanish on the real axis because particles are whizzing off to infinity. Instead, they vanish in the complex plane in what is called Stokes sectors here. Okay? And in this phase, eigenvalue problems have a global parity symmetry, P symmetry, but not PT or complex conjugation symmetry. And in this problem, we're describing unstable particles, particles that are going off to infinity, and so the energy eigenvalues of these particles are complex. Okay, this is like an unstable atom. Unstable atoms, you know, the states of an unstable atom are complex because the atom is decaying. Okay, but now let me show you phase 2, and this is the interesting part. But I want you to know, I want you to look and see that this is something I already talked about at the beginning of my talk. You remember I said when I started out, I talked about x squared times ix to the epsilon? In this case, what happens is, as I increase epsilon from 0 to 2, what happens is the region in the complex plane where the wave function goes to 0 rotates downward, and eventually the eigenfunctions vanish at infinity in a pair of what is called Stokes sectors that look like this. So as you go off to infinity in this direction and in this direction, that's where the eigenfunctions vanish. Okay? And you end up with real eigenvalues, okay? You end up, amazingly, with real eigenvalues, okay? And you can ask, how can an upside down, I want to go back just for a second. Yeah, let's, I was going to make a comment, but I think I won't. You end up, in the quantum mechanical calculation, with a completely different phase. Instead of complex eigenvalues, you have a real positive spectrum. And you can ask, how could a repulsive potential have a real positive spectrum? Well, it does. And I'm going to be showing you a picture of this spectrum, but I'm going to show you a 3-step proof that the eigenvalues are actually real and positive, okay? Now, I didn't say I was going to explain the proof. I said I'm going to show it to you, okay? So this is the first page. This is nothing more, actually, to be honest, this is no more complicated than what any freshman student can do. It just involves changes of variable and keeping track of minus signs and so on. But for this particular problem, I can give you a 3-step proof that the eigenvalues are real. Are you ready? This is the first page of the proof. This is the second page of the proof. This is the third page of the proof. Okay? And this is the final answer. Okay? This is the end of the proof. And that's it. That's all that's involved in the proof. But what I have proved is this in this proof. This is the Hamiltonian we started with, a minus x to the 4 potential. And in this proof, I show that the energy levels of this potential are exactly the same, exactly, not approximately, exactly the same as the eigenvalues of this potential. But this potential has a plus x to the 4 instead of a minus x to the 4. And as you know very well, there are bound states, and the bound states have real positive energies, and this is a Hermitian Hamiltonian, and therefore the energy levels of this strange upside-down potential here, which you wouldn't think could possibly be real, are real. So in one phase, the eigenvalues of this potential are actually real and positive and discrete. Okay, you have to understand, when I saw this happening, I was really kind of blown away. Wait. Can you comment on the parity anomaly? please ask me a question about it afterward. But I don't want to comment just yet because I know that people are very worried that this talk is going to be too long. And although I was told I could speak, when people invited me to come and give this talk, it was arranged that this would be an hour-and-a-half talk. And right now, it's 40 minutes old, and I was told just 5 minutes before I came up on stage that I would have 40 minutes to give this talk. Okay, so a little strange, but let's save that for afterward, okay? I hope you don't mind. So you remember this? Remember I talked about the motion being unidirectional, okay? We have been writing papers about unidirectional motion for many years. Here's some of the papers that I've written. But the most recent paper is an interesting paper that proposes an actual experiment that can be done to see this second phase in a laboratory. Okay, now, I should tell you that as you can guess, I'm a mathematical physicist, and as a mathematical physicist, I never expect anything I'm going to say to you or anything I'm going to write in a paper that I publish will actually be seen in a laboratory. That would be an amazing thing. And it didn't happen until I was working on PT symmetry. But about 7 years after I published my first paper on this subject, this was observed, PT symmetric Hamiltonians were observed in the laboratory. I couldn't even sleep that night. Okay, I got an email, said we saw the PT phase transition, and I just couldn't sleep. It was an amazing feeling. It never happened before to me. And hundreds of experiments have now been done on different aspects of PT symmetric systems, and we have just last year published a paper in Physical Review Letters, which we think is going to be carried out by an experimental group at the University of Toronto, where they will observe this PT reflectionless motion, and that they will observe the real positive eigenvalues of this kind of PT symmetric upside-down potential. Okay, so if you don't believe me, I will now show you an exact plot of what the energy levels look like. Okay, so here is the Hamiltonian that I've been talking about, p squared plus x squared times ix to the epsilon, where epsilon is real, okay? And when epsilon equals 0, you have the harmonic oscillator, and its eigenvalues are 1, 3, 5, 7, 9, and indeed, here's the epsilon axis. You go to 0, and these are the energy levels. And as epsilon increases, the eigenvalues all remain real. They vary as a function of epsilon, but all eigenvalues remain real, positive, and discrete. And that includes the upside potential at epsilon equals 2, which is the minus x to the 4 potential. And that's astonishing. It's absolutely amazing, okay? Because this Hamiltonian has a phase in which, even though it's upside down and it's a repulsive potential, it confines bound states. Okay? By the way, there is something in that picture that I didn't mention before, and that is that you can have a PT symmetric Hamiltonian that doesn't have all real eigenvalues, and that's a Hamiltonian with broken PT, okay? So let's go back and look at it more carefully. You notice that if epsilon goes below 0, to the left of 0, something funny seems to be happening. The eigenvalues come together in pairs, and they seem to disappear. Well, they haven't disappeared. They're still there, but now they're complex. So I call this a region of broken PT symmetry, and this is a region of unbroken PT symmetry. And there's a PT phase transition between the region of broken and unbroken PT symmetry. Okay, so broken and unbroken. Okay, and this can be seen in a laboratory. It's not subtle. Every experiment that is set about to look at this has found it immediately. It's as big as a church door, you know. You can't miss it. It's not subtle. Okay, so PT symmetric Hamiltonians are quite astonishing. And if you want to know where they belong in nature, well, there are basically three types of Hamiltonians. There is a Hermitian Hamiltonian. There is a non-Hermitian Hamiltonian, but in between, there is a PT symmetric Hamiltonian, okay? And there is, in fact, a transition between, that you're going to see in a laboratory, as I said, between parametric regions of broken and unbroken PT symmetry in a PT symmetric Hamiltonian. Okay? So I want to give you an intuitive explanation of the PT transition. And so this is just a very easy explanation. Almost anybody could understand this, including him. So I want you to imagine that you have a closed box, okay, just a box, and you're pouring stuff into this box, okay? You could be pouring water into the box, okay? Is this system in equilibrium? Well, no, of course not. It's filling up with water, right? So next, I want you to imagine two boxes. So I'm going to pour water into the first box, but I'm going to take water out of the second box. Is this system in equilibrium? Well, of course not. Water is filling up in the first box and it's draining out of the second box. It's not in equilibrium, okay? But what happens if I take a pipe and connect the boxes, okay? Then water can flow into this box. It can flow through the pipe into this box and then flow out. And if the pipe is wide enough, the water can equilibrate what is happening in the left box and the right box, the right box. And in this case, the system can be in equilibrium. Okay, well, you can do this quantum mechanically, and you can couple the boxes with a coupling constant G, and that system is described by this Hamiltonian here. And you can calculate the eigenvalues. And if you do, you find that the eigenvalues can either be real or complex, depending on how big the coupling G is, okay? So the energy, you know, there's a square root here. And because there's a square root, if G is a big number, then the square root of a positive number is real and the energies will be real. But if G is a small number, then the energies will be complex. So the system can have a transition between real eigenvalues and complex eigenvalues. Okay, so you notice that this system is a system of balanced loss and gain. You're pouring water into one box, so that box is gaining water. You're taking water out of the other box, so it's losing water. And if the coupling between the boxes is good enough, then the system can be in equilibrium and the energies can be real. And you don't have any growth or decay. The Hamiltonian is not Hermitian. No, the eigenvalues definitely are orthogonal, and you can ask me about that after my talk. Okay, not only are the eigenvalues orthogonal, but with a definition of what the dot product is, but the system is unitary, even though it is not Hermitian. And we can talk about that afterward. Happy to chat with you. These are, the only reason for showing you this slide is that this is a vast number of interesting Hamiltonians. For all these m's and all these n's, you understand, look at this. All these eigenvalues are real, strictly real, positive, and discrete. Okay, so here's just a brief summary of PT symmetric quantum theory. What I have done for you is to generalize quantum mechanics by replacing the mathematical, it's a very mathematical condition of hermiticity. And this sticks out. You know, when I took a course in quantum mechanics as an undergraduate, I listened to what the axioms of quantum mechanics are. And they all sound like they were written by a physicist. You know, positivity of the energy levels, you know, that there has to be a ground state in order to have stability. You have to have locality. You have to have causality. These are all physical requirements. And then you have this condition of hermiticity, and that appears to be written by a mathematician, okay? Not by a physicist. You know, transpose and complex conjugate, are you kidding? What does that have to do with physics? But PT symmetry, now that sounds like physics, because physicists love to talk about symmetries, okay? The bottom line of what I've been telling you is that if the Hamiltonian is PT symmetric, its eigenvalues can be real and positive, okay? And time evolution can be unitary, even though the Hamiltonian is not Hermitian. Okay, so what I've shown you is that PT symmetry combines the beautiful physical theory of quantum mechanics with the beautiful mathematical theory of complex variables. Okay, now, I was interested to know what ChatGPT had to say about this. So I got onto the computer and I connected to Chat and I said, please write a Shakespearean sonnet about PT symmetry. Okay, it took ChatGPT about a third of a second and it produced this. And I was absolutely blown away because, you know, there are many papers on PT symmetry, about 12,500 papers, and it read it all. And it says here, this is really extraordinary, it says, PT symmetry, a twofold guise, you see that? Where P reflects space, yet T in time. Together sing a tale of compromise, a quantum world, a balance. Get it? A balance, most sublime. Unbroken, you understand? I was just talking to you about broken PT symmetry. Unbroken, this domain of spectral dance. You know, it's talking about the spectrum here. The loss and gain of energy entwined. Remember the boxes? Their quantum states, a harmonizing trance, in eerie beauty, to each other bind, and thus, in deep embrace of mystic schemes, PT symmetric quantum magic gleams. Unbelievable. It took us a third of a second. If you asked me to write this thing, I'd be still working on it months afterward. Okay, so I want you to remember that there are three kinds of physical systems. One of them is a conventional Hermitian system that you learn about when you take a course in quantum mechanics. It is a closed system, okay? The other typical system you study, which is more difficult, is an open system. This is the kind of system you study when you learn about scattering theory. But PT symmetry lives in between, okay? Because PT symmetric systems are not Hermitian, but there is a balance between loss and gain, okay? And because of this balance, there's an entirely new kind of physical system which has these amazing properties that I've been talking about, okay? This is the very first work on PT symmetry, the experimental work that I told you. You remember I was telling you I couldn't sleep one night? Well, this is the paper that stopped me from sleeping for a night. And it appeared in PRL back in 2009. The main person on the experiment, Christodoulides, just won in 2023 the Laser Prize. And it was awarded for the fields of parity time non-Hermitian optics, okay, PT symmetric optics. And this is a second paper of his, which is published in Nature Physics, which is just a fantastically beautiful paper. I won't describe it to you. You can read it if you're interested. However, this is a more recent, very elementary, popular review article that appeared in 2016 and that I wrote. And in the art, there's a picture of the original experiment. This is the actual experiment on a laboratory table. I won't explain the experiment to you, but that's the experiment where they first observed PT symmetry. There's a comic picture that I can't not show you. It appeared in 2015, okay, in Nature Physics. It's a cartoon about the top 10 physics discoveries of the last 10 years, but it's full of jokes. But you have to read it carefully to see the jokes. I mean, it talks about the discovery of the Higgs boson here. Okay, not the Higgs boson, the Higgs boson. Okay, everything is misspelled. Up here is the discovery. This is party time symmetry. They left the I off parity time, and it came out as party time symmetry. Okay, now I'm going to skip this part of my talk. It's really cool, but I'm going to skip that. But I'm going to point out that it's very interesting that, let me go back just one. This is a quantum system that has not 2 phases, but 3 phases. And never mind how I got this, but the energy levels of each of the 3 phases here are small energy levels in the Hermitian phase. There is bigger energy levels in the first PT symmetric phase, and even bigger energy levels in the next PT symmetric phase. And that's very interesting because you know, if you've been reading just popular science, that there are 3 particles that are very similar. In fact, they're called the electron, the muon, and the tau. And these particles have exactly the same properties, except that they have different energies. 3 classes of particles with different energies. And I wonder whether or not we could show that these are 3 phases of the same Hamiltonian. Okay. Now, before I end this talk, because I have a real bang for you at the end, okay, and I'm almost at the end of the talk. But before I do, I think it's important that I should give you an overview of the talk so far. Okay, and so here it is. Okay, except there appears to be one person who actually didn't find it so, well, never mind. Okay, so I have only been talking to you about elementary quantum mechanics, but I could talk to you about quantum field theory, okay? Quantum field theory, not quantum mechanics. So this is the thing that's supposed to be describing the universe, and I have just a few slides, one or just a few, less than half a dozen, to show you about this. Now, of course, I'm not going to explain quantum field theory to you, okay? But I do want to point out, I'm going to skip this, but I'm going to point out that quantum field theory is based on space and time, okay? 3-dimensional space, 1-dimensional time, and Einstein told us all about it, and he pointed out that the Lorentz group is fundamental. And what you learn in elementary physics is that the Lorentz group is the set of all 4x4 matrices that transform the space-time point, okay, x, y, z, and t, into x prime, y prime, z prime, and t prime in such a way that x squared plus y squared plus z squared minus t squared is preserved. Okay, this is the basis of quantum field theory. Okay, and that's called the light cone condition. And by the way, as I'm sure you know, P and T, parity and time reversal, are elements of the Lorentz group. Why is that? Because P reverses x, y, and z, changes it to minus x, minus y, reflects them. Okay? Time reversal changes the sign of t. But in this condition over here, everything is squared. So, of course, you don't have to worry about the minus sign. Okay. The complex Lorentz group is very interesting. And what happens is it takes the ordinary Lorentz group and it shows that there is a connection between the elements, oh, let me go back, the elements in the conventional proper orthochronous Lorentz group with all of those elements multiplied by pt. In other words, if you look in relativity, special relativity, you can see that the whole concept of pt symmetry is in fact already there. It was there just for the taking. Okay? All you had to do is draw a picture of the Lorentz group and think about it for a couple of minutes, and you realize that it is everything I've said, essentially, is all there. Okay? However, no one picked up on it. I don't know. Okay? Now I'm going to conclude with just a discussion of two different theories. One of them is the theory of electrodynamics, and one of them is the theory of gravity. Okay? So in electrodynamics, I don't know if you have studied quantum electrodynamics, but a long time ago, a very smart guy who is a very good friend of mine had an idea. This was back in 1952. It's not a calculation. It wasn't a theory. It wasn't a theorem that he proved, but it was a suggestion. It was a conjecture. And what he said was, in electrodynamics, what happens if we take the electric charge and replace it by I times the electric charge? Well, of course, that's silly, because you can't do such a thing. The electric charge is a fundamental quantity. But he said, never mind, just replace E by I times E. Well, that means that alpha, which is the fine structure constant, which is the square of E, becomes negative. And that means that Coulomb force changes sign. Okay? So you know, because of the Coulomb force, that a positive charge and a negative charge attract each other. They're pulled toward each other. But if you replace E by I times E, and you change alpha into minus alpha, a positive charge and a negative charge repel. Okay? So Dyson argued that when you do perturbation theory in electrodynamics, which involves a series and powers of alpha, okay, when alpha is positive, you have a stable universe. But when alpha is negative, you have an unstable universe, and positive and negative charges are repelling each other out to infinity, and we're all dead. Okay? So somewhere, namely at alpha equals 0, we must be talking about something that is not analytic, and therefore perturbation series diverges. Okay? Because a perturbation series is a Taylor series in powers of alpha. Okay. That was a conjectural paper. In fact, Dyson is completely right. That a perturbation series is always, in alpha, is always going to be a divergent series. But he's wrong about the reason. He's completely wrong about the reason. And Dyson he's a very famous physicist. He was a very good old friend of mine. We knew each other for many years. I met him when I was at the Institute in Princeton, and I took a long trip down to Princeton to explain to him that perturbation series do indeed diverge, he's right, but not for his reason, okay? They diverge simply because there are many Feynman diagrams. In fact, the number of Feynman diagrams grows factorially, okay? It's a very simple reason. In fact, a theory in which alpha is negative is just like the theory that I spoke to you about with that elementary negative x to the 4 model, where you have a stable phase, okay? So I claim that electrodynamics with a negative sign of alpha actually has 2 phases, okay? There is the obvious phase in which we all die because the universe is blowing off to infinity. It's repelled off to infinity. But there is a stable PT-symmetric phase of electrodynamics in which the spectrum is real, and I've written a number of papers on this, which I won't go into detail on at all, okay? But I'm claiming that there are, in fact, 2 phases. Okay, this is the very last thing I'm going to talk about. I want to mention gravity just briefly, okay? So, you know, gravity started out, you know very well, this is Newton sitting under an apple tree, and you know the rest. Okay, but then Einstein came along, and this is a picture of Einstein. He has just proved that time is actually money. Okay, so I'm going to conjecture that, like quantum electrodynamics, classical and quantum gravity actually occur in 2 phases and not 1. There's phase 1, in which gravity is Hermitian, and g mu nu, the metric tensor, is a tensor. But there's a second phase, which is a PT-symmetric phase of gravity, in which g mu nu is not a tensor, but an axial tensor. Phase 1 is conventional gravity, which is real and attractive. But in phase 2, gravity is complex and repulsive. And this could explain the accelerating expansion of the universe. That is something that is called dark energy. So at short distances, I'm conjecturing that gravity is attractive. That's the attractive phase of gravity. But at great distances, gravity is repulsive, and it is a PT-symmetric phase of gravity, okay? And I'm going to show you one picture, which is a toy model of a toy model of a toy model. It is a very simple idea. Gravity is a 3-dimensional, lives in 3 space dimensions, okay? And gravity, the gravitational potential is 1 over r. So it involves x, y, and z. It's very complicated. But I'm going to show you a 1-dimensional picture of that. This is a picture of a Hamiltonian. Instead of 1 over r, I'm just going to write 1 over x. And I'm only going to talk about a 1-dimensional, gravity on a 1-dimensional line, not gravity in a 3-dimensional space. So this Hamiltonian has a turning point, and the turning point is right over here. But it also has a pole at x equals 0, which is right here. And I claim that poles repel, but turning points attract. So if you have a particle that comes in, let's say, from infinity, it's pulled around, okay? This particle is, this could be the motion of some asteroid or something. It's coming in from infinity. It's pulled by this turning point, and then it goes back out to infinity. That's the attractive phase of gravity. But because this has a singularity at 0, it has a repulsive phase as well, and all the particles out here they're flowing along here, and they're pushed away by this pole, and they travel out here. So we have two regions of space, a distant region out here, a distant region where particles are traveling away, and another region here where particles are pulled in, okay? And we wrote a paper on this, and we can go into detail about it. But there's a very interesting paper that just appeared based on this work. This was published by two friends of mine with whom I've written a lot of papers. Their names are Mavromatos and Sarkar. And in this paper, they argued that a complicated quantum theory of gravity, that is a Chern-Simons gravity theory, may have two phases, and they study a string-inspired effective axion theory in which gravity is anomalously coupled to abelian gauge fields, okay? So this is a very complicated paper, and I wouldn't even begin to discuss it here with you. M&S, by the way, they are in England, but this is not Marks and Spencer, okay? So M&S claim that the renormalization group analysis suggests that there's a pole that separates two phases. There is a short distance phase, which is a Hermitian phase of gravity with attractive gravity, and a long distance PT symmetric phase, which has a repulsive gravity. And you can read that paper. It's a very fancy, difficult paper, but I think that it is just beginning to scratch the surface. It is in no sense a proof of what I'm claiming. Okay, so just to let you know, lots and lots of people have joined in. I originated the theory of PT symmetry back in 1998. And this is the publication rate per year, and this is where the experiments were first being performed, and the publication rate has zoomed up. There are now, not counting papers on the archive, there are now 12,500 papers published so far. So there's lots and lots and lots of work to be done. PT symmetry provides a very wide range of fresh, new theoretical and experimental research problems for you to solve. And thank you so much for listening to the talk. And I'm happy to answer questions.
Hello, can you hear me? Okay, let's start with questions. Over here, if you can please say your name and stand up.
Yeah, my name is Ahmed. I have many questions actually. So, first
Let me just say, whenever I give this talk, people have many, many, many questions. Okay.
Yeah.
And
to be
typically,
honest,
people stay after. When I give a colloquium in this, they stay after at least an hour to ask questions.
Yeah. So I'm just gonna be honest. I don't buy most of this. I have a lot of issues. Standard model. I think if you look into Higgs model, you renormalize, you'll get some extra terms that you don't know how to deal with. So that just suggests a lot of instabilities.
I didn't quite get that.
So
if I look at the Higgs model.
Yeah, and you renormalize, I'm assuming you'd get some like 5/4 log term. So
Well, yes, but I don't understand what you're saying. If I look
yeah,
at
if you look into that, then you don't know how your vacuum behaves. Your vacuum would be very unstable, which is, I mean,
yes,
unless,
that is the okay. This is actually you are asking. I'm not sure that we should have a discussion about. I mean, I gave a talk primarily focused on elementary quantum mechanics and elementary classical mechanics. I really don't think that we should subject the entire audience. I'm happy to talk with you at great length afterward about the Higgs model, but I don't want to get into a technical discussion because most people, I think, in this audience have not studied the Higgs model, and I don't want to have a private conversation with you in the public where there are, I don't know, many scores of people listening to our private, personal discussion. Do you have a general question about what I...
we can go back to the coupled Hamiltonian. I have a question about that. So you ended up getting ended up getting like eigenvalues that depend on G. So one eigenvalue go up, another eigenvalue go down. In the weak coupled, if G is small, then I'm assuming you.
Wait, I'm having trouble. Which Hamiltonian are we discussing now?
When you had like two non-interacting systems, A plus IB, A minus IB, G and G. So your eigenvalues go up and down. It's a non-equilibrium system, right? And so this is a clarifying question for me. So basically, your system would be in equilibrium if G is big enough, like if the system is strongly coupled.
If G is large enough. If G squared, technically,
if G squared is high.
If in absolute value G is large enough. And if G is not, then indeed you can have complex eigenvalues. Yes, that's right.
Okay, and I wanted to know more about the parity anomaly as well. What interpretation do you have for Z?
Okay, so I used a word. Okay, that doesn't have an anomaly. Okay, so you're asking, you've combined two things that are not related. You asked me about the parity anomaly, but you also asked me about this quantum mechanical system. They have nothing to do with each other. The parity anomaly, so an anomaly, okay, so an anomaly is a pure quantum effect. An anomaly is the word that is used to describe a physical effect which disappears in the limit as Planck's constant goes to 0. Okay, that's the meaning of an anomaly. The point here is that in my mathematical proof, in the rigorous proof that the eigenvalues of this upside-down potential are real, I showed that the original upside-down Hamiltonian has exactly the same eigenvalues as a right-side-up Hamiltonian, but that right-side-up Hamiltonian is not a classical Hamiltonian because it contains Planck's constant. Okay, now, once again, an anomaly is a very sophisticated idea, and I don't want to, I mean, you and I would be delighted to have a private talk with you and discuss the meaning of a quantum anomaly. And, you know, in physics, there are books about quantum anomalies, and I don't want to sick that on the rest of the audience unless there's an overwhelming interest in quantum anomalies, okay? So I just mentioned it in passing, okay? But I'd be most happy to talk with you about that.
Hi, yeah, we have one question back here. Let's make
And
it quick.
I think that's going to be our last question. Then after that, if anybody has any remaining questions, if you can please come up and talk to the speaker. Thank y'all.
Ladies and gentlemen, thank you for staying for the full duration of that. I do have one important announcement. I would like you to check to see if you are in possession of a Capital One blue Visa card. One was lost. If you realize you do not have it, come see me so I can verify it's yours. Thank you for this talk, and we will continue with the program. Thank you. Please be sure to scan your QR code to give your evaluation of each session. So please take this time to do your QR code and fill out your evaluation. Thank you.